Exactly so. So here we've got 3 different toppings. So we have 2 to the power 3 different possible pizzas on offer at Power Pizzas Inc. Or if we want to write it down as a formula, what your colleague just said here in the front row will be written like that. Okay? So the number of elements, or to use the technical term, the cardinality of the power set, is just 2 to the power of the number of elements in the base set, the original set, the topping set, if you think of our pizza parlor. Right, so that's the power set. Now there's something else that begins with P. And here's a little gotcha. Many people, I think it's because they both begin with P that people confuse them, and they're also to do with subsets. But it is not the same. This is something different. So this is the idea of a partition. We've seen a simple idea of a partition of a set into 2 parts right at the start of when we started talking about sizes. So here's the more general idea. If we have a set, we can split it up not just into 2 parts, but perhaps into a whole series of parts, P1, P2, P3, each of which is a non-empty subset of the original set S. And here are the requirements. First of all, if you join them all up back together again, but with union, so P1, union P2, union P3, etc., then you do recover the whole of the original set. So the PIs between them cover all the elements in S. On the other hand, none of these subsets overlaps. So everything is included, but everything is included only once in each of these subsets. So this subscripting device is a fancy way of saying if you take any 2 of these subsets, their intersection will be empty. So all pairs of subsets of this joint, they have nothing in common. So 1 or 2 little simple facts to observe about partition. Let's illustrate this second one, jump straight into the example. So here's an everyday example. We move from the pizza parlor back to the office now, the lunch break is over. And if we go into a building where, let us say, 3 employees work, it's a small building, and the 3 employees who work there are called M, N, and O, or to be a little more friendly, Mark, Nora, and Olaf. I choose this example because of the partition. If you have a building, and it's an open plan office at the moment, well, how are you going to make offices in it? Well, you put a partition in it. Okay. So notice what are the possible choices here. We could indeed have the everybody in one big office solution. So we've got Mark, Nora, and Olaf all sharing one office. Note the double braces here. So this is a set of subsets, just that there is only one subset. So the inner sets are sets of people who share one office. The outer set is the set of all office forms. Okay. So here is another partition. This time we put Mark and Nora sharing an office, and Olaf gets the office by himself. And at the opposite extreme, here's the solution where everybody gets an individual office. So each of these, in this case, 5 different configurations, each of those is a partition. Each of them separately, we say, is a partition of the original set, Mark, Nora, Olaf. It's a way of assigning the employees to each to a subset office. You don't put somebody in more than one office. Everybody has exactly one office, but you don't leave anybody out. Those are the 2 conditions we gave in the definition. Okay, we can wrap things up more or less on time, just 25 past now, and we've caught up with ourselves. You might think not if you look ahead to the next slide, but as you'll see, that will be the case. This top item here, we've already said, this little observation, that every element in the original set is included in exactly one of the subsets in partition. This little notation means there exists one, there exists a unique. And there's one little thing, we won't have time for discussion now, perhaps we'll pick it up at the practical classes. If we didn't have that notation, would we be stuck, or would we have some other way of saying it? Well, we could say it another way, but it'd be a bit more long-winded. The final thing, and don't think about this, the reason I'm giving you this is twofold. First, well, three actually, let me say three things. First of all, I do not expect you to know this. I do not expect you to remember it. You don't need to commit it to memory. I wanted to show you this. This is the way of defining, well, how many different partitions could we have if there are n employees, if there are n elements in the original set. And what I wanted to show you this for is to make the point, not all mathematical problems have a simple closed formula that just comes out as an A squared or something. No, some things are more complicated than that. And this is like a little recursive program to tell you how many partitions there are. So, just to do a reality check here, let's say not all mathematical problems have a simple formula as their solution. So, those are 2 points I wanted to make, and at that point we should wrap things up. Now, notice, for your encouragement, we are halfway there. That is the close of the first block of lectures. That's 6 lectures done. There's been problems this week, of course.